Hey everybody, welcome back to chemistry. And so we are continuing on through chapter 6. And so now what we're going to do is we're going to look at different definitions of energy. There is a particular new definition of energy we're going to be looking at, which is enthalpy. So I sort of have a slide here that sort of describes what I'm going to be saying on the board right now. So you already know one definition of energy, and so that is internal energy here. And so internal energy, the letter that symbolizes it is U, but in other books it could be E. And so either one of these is internal energy. And so it's an energy, and so it's going to be measured in joules. Now there's a different kind of energy you can measure with molecules, and then this kind of energy is called enthalpy. The variable for that is the letter H, but it is a kind of energy, and so we can measure that as joules as well. So to sort of explain the differences between enthalpy and internal energy, I kind of think it's easier to focus on the differences between the change of internal energy of a reaction versus the change of enthalpy of a reaction. So that's what I'm going to sort of talk about now. So let's think of some sort of simple example here. So let's say that you have a beaker here, and let's say the beaker is just full of chemicals, and let's say that you have a couple of reactants, which are A and B, and let's say you, in some fashion, start A to react with B, you get a reaction going, and those reactants are converted to products, which are C and D. Now, it could be, for example, that A and B have a lot more chemical energy than C and D do. And so if that's the case, then that extra energy that A and B have must be released to produce C and D. And so let's say that you see two forms of energy that are released by this reaction. So one form is Q, and the other form released by this reaction is W. So Q is the heat released by the reaction. We'll give it a value here. And let's say that Q is negative 250 joules. So work here is the work that the chemical reaction is doing on the surroundings. And so we'll give it a value of, say, negative 150 joules. Okay, so let's look at these values here. So what we have is we have Q, and we have W. And so Q is negative 250 joules, and W is negative 150 joules. And so again, these are the two forms of energy that are released as you move reactants to products. And so you can add them up here. And so what you can see is that the total amount of energy that is produced by this reaction is what? Negative 400 joules. Now, one of the things you learn is that the amount of heat and work produced here in a chemical reaction is going to be equal to the change of internal energy of the chemical reaction. So let me write here, the change of internal energy is delta U for the reaction. So that tells us is that the total amount of energy being produced by this reaction is negative 400 joules, that the change of internal energy of the chemical reaction is also going to be negative 400 joules. And that kind of makes sense because you might remember that the change of internal energy of a chemical reaction is going to be the final energy of the products minus the initial energy of the reactants. And so the products here must have 400 joules of energy less than the reactants, and so the change of internal energy of the reaction must be negative 400 joules. Okay, so we just figured out what the change of internal energy of the reaction is, okay? So just to point out, a lot of times chemists just will have a chemical reaction, and for whatever reason, they just don't care about any work that the reaction may be doing on the surroundings or any work that the surroundings are doing on the chemical reaction. So the work is occurring, but they just kind of ignore the work. And they're just kind of focusing here on any kind of heat that is absorbed or released by the chemical reaction. So let's say you're your average chemist here and you just don't care about the work. The work is going on, but you just ignore it. You just kind of focused on the heat here. Okay, so you're focused on the heat, and so it's the same chemical reaction. Again, you're ignoring the work. You're just looking at the heat, and it's negative 250 joules. Okay, so what is the heat? Well, you can see that if the total change of internal energy of this reaction accounted for heat and work, you can see that not all of the internal energy change is going to account for heat. And so it's going to be a fraction of the change of internal energy that's going to account for heat. And so you can see of the negative 400 joules of internal energy change that accounted for heat and work, it's only going to be negative 250 joules of that internal energy change that will account for heat. Well, that fraction of the internal energy change that counts only for the heat is called the change of enthalpy for the reaction. Okay, you can sort of see the difference now between the internal energy change for the reaction versus the enthalpy change of the reaction. Again, the internal energy change of the reaction will account for both heat and work, but only the enthalpy change of the reaction accounts for the heat. Now, another thing I need to mention is a lot of times chemical reactions are just carried out sort of maybe on a tabletop. And so as the chemical reaction is occurring, you have constant pressure. And so here you have this energy that is being produced under constant pressure. And so we sort of add a little bit more detail here to this. And so we have delta H of the reaction is going to be equal to the heat released or absorbed, but at constant pressure. So a lot of times you'll see it's going to be equal to Q sub P. And so just note the sub P means it's constant pressure. So now what I want to do is talk about how close the change of enthalpy of the reaction could be to the change of internal energy of the reaction. So as you'll see in a bit, most of the time the value of the enthalpy change of the reaction is actually a number that is very close to the value of the internal energy change of the reaction. But occasionally you'll have a reaction where the enthalpy change of the reaction has the same value as the internal energy change of the reaction. So I want to talk about when that occurs. So let me sort of give you an example here. So let's say you have a beaker here, and let's say it has chemicals in it. And so this time you're reacting E and F, and it's producing G and H. All right. So let's say that you sort of are observing this reaction, and then you sort of watch the reaction and see that there is no change of volume here as this reaction goes. So you can say delta V is 0. And the reason is delta V is 0 is because the volume of the products, for example, is going to be exactly the same as the volume of the reactants. Okay, so when you have a chemical reaction and the change of volume is 0, under these conditions, then you will find that the internal energy change of the reaction is going to be equal to the change of enthalpy of the reaction. So let me talk about how that is possible. Okay, so again, imagine this chemical reaction. And so heat is being produced here, and so let's say we have Q here and it's negative 500 joules. But again, because the volume is not changing in this chemical reaction, the work is 0. Okay, how could it be that the change of enthalpy is going to be the same as the change of internal energy? Well, let's look at the formula for the change of internal energy of the reaction. So you know what that is the change of internal energy of the reaction is going to be equal to heat plus work. Now, maybe one of the things you learned earlier is that work is going to be equal to negative P, which is pressure, times the change in volume. And so we can substitute in negative P delta V into work. And so you can write this. The change of reaction is equal to Q minus P delta V. Okay? So let's say there is no volume change in this reaction. Okay, so the volume change of the reaction, we'll say, is 0. And now if that's the case, then you can see that the change of internal energy of the reaction is just going to be equal to Q. Now, you already know that we've defined the change of enthalpy of the reaction to be equal to Q. So under these conditions, when the volume change of the reaction is 0, then I think you just figured out that the change of the internal energy of the reaction is going to be equal to the change of enthalpy of the reaction. There we go. So now let me just kind of give you an actual example of a chemical reaction where the change of volume is 0. So let me erase this information here. So this situation occurs during the combustion of methane. And so here what happens is methane reacts with oxygen. So let me go ahead and write out a balanced equation for that. So it's going to be CH4 plus O2 gives you carbon dioxide plus water. And so we have to balance it. And so I think you work this out. What you would find is I think you have to put a 2 here in front of the water and a 2 here in front of the oxygen. So now let's consider the number of moles of reactants we have and compare it to the number of moles of products. And so I think what you can see here is that we have a total of 3 moles of reactants and we have a total of 3 moles of products. Now, one thing to keep in mind, as sort of seen on the screen, is that each of these reactants and products are gases. And so what you can imagine is that each of these gases will occupy a certain amount of space. Now, as it turns out, 1 mole of gas at room temperature and pressure occupies approximately 24 liters of space. Now, if you double the amount of moles of gas, you will double the volume. So if you have 2 moles of gas, that will occupy about 48 liters of space. If you triple the moles of gas, you triple the volume, which is 72 liters. And so what you can see is for these reactants, if you have 3 moles, that will occupy 72 liters of space. When those reactants are completely converted to products, they also occupy 72 liters of space. And so in this particular reaction, delta V is equal to 0. So what you can see here that while the internal energy change of the reaction is going to be equal to Q plus work, that is going to be equal to Q minus P delta V. And so this delta V is 0, so it's Q minus 0, so it's equal to Q. And you've already learned that Q is equal to delta H of the reaction. And so you might expect that the internal energy change of the reaction is equal to the enthalpy change of the reaction. Okay, so let's move on. So most of the time, though, when you're carrying out chemical reactions, a little bit of work will be done. And the reason is maybe the volume increases as you're going from reactants to products, or maybe the volume decreases as you go from reactants to products. And so let me just kind of give you another example of that. Okay, just to sort of point out here on this slide that if you have a chemical reaction and volume is increasing, maybe because you have more product volume than you have reactant volume, then you're going to have the system doing work on the surroundings. And if so, then you're going to find that the change of enthalpy of the reaction, which only accounts for Q, is going to be different than the change of internal energy for the reaction, which is accounted for by Q and W. Another possibility is that you have a chemical reaction and you find that maybe the reactants have more volume than the products, and therefore it seems like now the gases are compressing in the reaction. If so, then you have work being done on the system by the surroundings. And so that again will affect the change of internal energy of the reaction. It'll make it different than the change of enthalpy of the reaction. So we sort of have an example of that here. So we have a chemical reaction here, which I'm going to write out, which is you have butane, which is in the gaseous state, and it's reacting with oxygen, which is in the gaseous state. And that will give us carbon dioxide in the gaseous state plus water in the gaseous state. Okay, and so what I'm going to do is just balance it. And so I'm going to put a 2 in front of here, a 13 in front of oxygen, and then we have 8 in front of carbon dioxide. and we have 10 in front of water. Okay, so the question is, do you think the volume of this reaction is changing as it goes to completion? And I think the answer will be yes. And the reason why I see that is because while you have 15 moles of reactants, you have 18 moles of products. And so I worked out what volume that is. And so 15 moles of reactants is 360 liters. And then 18 moles of products is 432 liters. And so we would expect in this particular reaction, some work is being done by the chemical reaction on the surroundings. So let's go ahead now and calculate what the change of internal energy of this reaction is and the change of enthalpy of this reaction is from the information I have in the problem. We have Q, which is 5,316 kilojoules. And so I think if you read the problem, it suggests that we have the chemical reaction is producing heat, and so this is an exothermic reaction, and so then we put a negative sign here. Also, work is being done by the chemical reaction on the surroundings, and so here, if that is the case, work is going to be negative, and it's 6 kilojoules. And so now you can actually calculate the change of internal energy of the reaction and the change of enthalpy of the reaction. So the change of internal energy is just going to be Q plus W. So it's going to be negative 5,322 kilojoules. And then the change of enthalpy of the reaction is just going to be equal to Q. And so that is going to be negative 5,316 kilojoules. So you can see that the change of enthalpy of the reaction is very close to the change of internal energy of the reaction. And I think if you sort of figured out what that difference is, you would find that those numbers are about 0.1% of each other. And so typically when you have chemical reactions, usually the change of enthalpy will be different than the change of internal energy, and it's almost always going to be less than 5%. Here the difference is much less than that, it's about 0.1%. Okay, so we move on. So one thing you have to be aware of is the following. If you're calculating a change of enthalpy for the reaction and that value is negative, that tells you that the enthalpy of the reactants was greater than the enthalpy of the products. And if that's the case, then it was an exothermic reaction. And so that would correspond to a reaction where Q is negative. On the other hand, let's say you have a situation where you calculate the change of enthalpy for the reaction and you find that the value is positive. Well, what that indicates is that then the enthalpy of the products is greater than the enthalpy of the reactants. If that's the case, then it would be an endothermic reaction and the Q of the reaction will be positive. Now, one thing you're going to have to do is you're going to have to look at diagrams of endothermic versus exothermic reactions in terms of enthalpy and interpret them. So I want to talk a little bit about that now. Okay. So let's take a look at sort of our standard exothermic reaction. So here I'm going to write exothermic reaction. And so what I have on the screen there is the combustion of propane. So propane is C3H8, and it's going to react with oxygen, and it produces carbon dioxide and water. Okay, so I'm going to leave out state symbols just to make my life a little bit easier with this problem. Now let's go ahead and balance the equation. So when I balance it, I need to put a 3 here in front of the carbon dioxide, it looks like, a 4 in front of the water, and then a 5 in front of the oxygen. Okay, so now what I want to do is construct something called an energy diagram for this reaction. So I'm going to actually prepare 2 energy diagrams. And so one energy diagram will have a fairly significant y-axis, but a kind of limited x-axis here. Then the other energy diagram has a significant y-axis with a more extended x-axis. Now, on the y-axis, what we're going to do is plot enthalpy. Now, note, I'm plotting H, enthalpy. I'm not plotting delta H. I am plotting H. And the same thing will be true for the other axis here. Okay, so let's go ahead and fill in this first diagram for an exothermic reaction. So here in an exothermic reaction, what must be the case is that your reactants here must have a higher initial enthalpy than the products. The products' enthalpy will be down here. So let me just kind of write that in. We have reactants and we have products. So this will be true for an exothermic reaction. And so let me just indicate what the reactants are. So we have C3H8, which is propane and oxygen. And then we have carbon dioxide and water as products. Okay, so let's say we want to indicate what the change of enthalpy is in this diagram, okay? So we're going from reactants to products, and you can see that the enthalpy is falling. So we're going from here, the reactants, to here, the products. So the change of enthalpy is this difference here between the H of the reactants and the H of the products. And so we can actually write this out a little bit more in that the change of enthalpy of the reaction will be the enthalpy of the final minus the enthalpy of the initial. And so another way you can write that is like this. The final, again, is just products, so it's going to be enthalpy of the products minus the enthalpy of the reactants. Okay, and so let's figure out what the sign of the change of enthalpy of the reaction is. And I think you can sort of see that because the products have less value of H, of enthalpy, than the reactants, you're taking a small number and subtracting a large number. And so the change of enthalpy for the reaction should be negative. And again, this indicates that we have an exothermic reaction. And so you've learned that the change of enthalpy of the reaction is equal to the heat released, right? And so Q will also be negative. Okay, so now let's go ahead and write into this diagram a little bit more detail. So now we have an extended x-axis, and this is something called the reaction coordinate. So the reaction coordinate is a time axis, and so let's go ahead and sort of imagine how this reaction is occurring. So here in my left fist here we have a propane molecule, and then in my right fist what we have is an oxygen molecule. And so what we're going to do is follow the level of energy as these molecules approach each other, react, and produce products. And so propane and oxygen have relatively high amounts of energy. And so as they get closer and closer, they still have relatively high amounts of energy. But then what will have to happen is when they strike each other, you have to break the bonds within the propane and within the oxygen molecule to release the atoms so that they can rearrange and form the products, carbon dioxide and water. Well, the energy you need to break those bonds is a little bit more than the energy that is within those molecules. That energy that is needed to break those bonds initially has to come from the outside, say from a burner, for example. And so that extra energy that is needed to break those bonds to release the atoms so that they can rearrange is called the activation energy. But then when you form the molecules, carbon dioxide, water, they will have far less energy than the reactants. So how can we sort of write this into here, into this diagram? And so here again we'll have the reactants here. So we have reactants, and we have propane and oxygen. And then here we have products. And we have carbon dioxide and water. Okay, so here we start out with reactants, and they have relatively high energy, and I'm just following the energy of the molecules over time. And then as I kind of mentioned, they need a little bit more energy to break the bonds. But then once you get over that hump where you have the molecules as atoms and form products, the energy of the products is lower, and so it goes down here. And so this is a nice detailed representation of an exothermic reaction. Now, from this diagram, you can figure out what the change of enthalpy is, and so let me show you how to do that. And so what is the change of enthalpy? The the change of enthalpy, again, is just the difference of enthalpy of the reactants from the products. So if we go over here, here is the approximate enthalpy of the reactants. And so here is the approximate enthalpy of the products. And so the change of enthalpy of the reactants versus the products here is delta H. Okay, now what is this bump of energy here? Again, this bump of energy here is called the activation energy. And so the activation energy is the difference between the energy of the reactants and the energy you need at the top of the reaction to get bonds to break. So this difference here is something called activation energy. And its abbreviation is EA. So you can sort of imagine this maybe if you've ever worked in a lab. And so let's say you have a Bunsen burner and you turn on the propane gas. And so if you release the gas into the air, which has oxygen, nothing really happens. There's no burning of the gas. We don't see any flame. So we need to add extra energy to get a flame. And so the way we do that is we spark the molecules. And so the spark provides the extra activation energy to allow the bonds in the propane, the oxygen molecules to break. And then you get the atoms reforming to produce carbon dioxide and water. But once that is going, then the natural energy of the reaction that is produced will be far more than is needed than the activation energy to carry on the reaction. Okay, so this is an exothermic reaction. Now let's go ahead and do the same thing for an endothermic reaction. Okay, so now let's go ahead and look at the energy diagrams for an endothermic reaction. And so we have that here on the slide. And so let me write out this reaction here. So this is an endothermic reaction. And here the reaction is taking ammonium nitrate, ionic salt, and adding it to water and having it dissociate to produce ammonium ions and nitrate ions. And so what I'm going to do is I'm just going to leave out state symbols to make my life easier. And I think you can sort of see right now that this is a balanced equation. Okay, so first off, why is this an endothermic reaction? Well, we know it's an endothermic reaction because when we add the ammonium nitrate to the water cools down. This suggests that what's going on is that this ammonium nitrate has relatively low chemical energy and has to absorb energy from the surroundings in the form of heat. And then when it has absorbed the energy, then it can dissociate to produce the ammonium and nitrate ions. Okay, so let me just draw two diagrams for this. Diagram like this, and then this more extended one. So on the y-axis, we have enthalpy again. Okay, again, here, the ammonium nitrate reactants have relatively low energy, and that must be the case because they have to absorb heat from the surroundings, the water, to separate into ions. Okay, so here is the enthalpy of the reactants. So I'm going to write reactants here. And so let me write out the reactants. It's NH4NO3 is the ammonium nitrate salt. And then here is the enthalpy of the products, which are the ions, NH4 plus NO3 minus. Okay. Now, what we can do is on this diagram, we can show you how you figure out the change of the enthalpy of the reaction. And so the change of the enthalpy of the reaction is just the difference in enthalpy of the products from the reactants. And so we're going from reactants to products, so I'll draw the arrow like this. So here the change of the enthalpy of the reaction is, again, this difference in energy between the reactants and products. So the change of enthalpy of the reaction is going to be equal to the enthalpy of the final minus the enthalpy of the initial. So it's going to be change the enthalpy of the reaction is just going to be the enthalpy of the products minus the enthalpy of the reactants. Okay, now let's figure out what the sign of the change of the enthalpy of this endothermic reaction is. Well, I think you can sort of see here is that we will have more energy in the products than we do in the reactants. And so if that's the case, then the enthalpy of the products will be a larger value than the enthalpy of the reactants. And so I think you can see the change the enthalpy of reaction of a endothermic reaction will be positive. Now you also remember that the change of enthalpy of the reaction is going to be equal to Q. And so if the change of enthalpy of the reaction has a positive sign, then Q has a positive sign, which we already learned is true for an endothermic reaction. Okay, so now let's draw a more detailed picture or diagram of this chemical reaction. And so here we have a time axis, which we call the reaction coordinate. So here is the relative energy of the reactants, which is ammonium nitrate. And here is the relative energy of the products, which are the ammonium ions and the nitrate ions. Okay, so what happens is this, is that, again, the ammonium nitrate salt has relatively low energy, and it's got to absorb heat from the water such that the bonds between the ammonium nitrate ions can break to release these ions which have relatively high energy. So it looks something like this. And so here we start out, and then heat is going into the ammonium nitrate salt, and then when the heat is enough, it can break the ionic bonds between the nitrate and the ammonium ions. And so that part there is sort of the highest energy. But then what happens is when the ammonium and nitrate ions are released, what will happen is nearby water molecules will form weak bonds with it. And whenever you form bonds, that tends to release energy from the molecules or ions. And so the energy of the ions will be a little bit lower after they have formed bonds with water. So this is sort of a nice diagram of an endothermic reaction. So on this diagram, let's see how we show the change of enthalpy of the reactant. So we're going from here reactants to products. So we have a delta H of the reaction. So if you wanted to, what you could do is add into this diagram an indication where the activation energy is measured. And so the activation energy is just the energy needed to take reactants and get them through this hump to become products. And so the activation energy is from here all the way to the top of the hump of the energy diagram here. So this is the activation energy. Thank you for listening, and we'll see you next time.